All right, welcome. So I have been able to finally post the information on the final project. So please make sure that you go through that. So the first thing is you need to do a project proposal idea and submit that. In that, the requirements are that the idea is that you're inventing a sensor system. What you're doing in here for the final project is just simulate it. If you want to do extra credit, you're welcome to even build it now and come and demo that. If you want to attempt even to build it, that would be extra credit. So if that sounds fun to you to try to get that done by October 3rd, you're welcome to also build it. But as far as the requirements, it just needs to be a simulation portion. So the simulation is, actually going back, it must use one sensor and then either at least one op-amp, which would be your comparator, or digital logic. So if you're not as comfortable with the comparator, you can do digital logic instead. Sensors are going to be something that if you're not in the lab, you can just make the assumption of, okay, I'm using the information that we've done in class and using that for the sensor values. So we had gone over in class about the, I think it was the thermistor. One of them, yeah, hot and cold. So when it's hot, it's like 15 kiloohms, and when it's cold, it's 8 kiloohms. So then you can use those values in your simulation and show that when I have 15 kiloohms, this is my output, and when I have 8 kiloohms, this is my output. And so those would be your sensor, and in those that you are taking lab, you can use any of the sensors you've looked at there, or if you want to start looking at a new one, you can start to measure it, find out the differences for different conditions, and then use those values in your simulation. Then the op-amp or comparator, the comparator or the digital logic. So when you're doing that, we talked about how do you convert that into a digital logic. So those sensors then are going to be read by through usually voltage dividers are going to be the easiest system to set up. And if you take measurements between two different locations, one a reference and then one of that, you can get a wider range of values to give you more of a high and a low value. So that would be a way to get it into digital logic. Or if you want to do it through the comparator, when it's high or low, then you could have your comparator either give some type of an output. So that's the other condition, is that you need it to output a signal of some sort. So it needs to light up a light, or it needs to turn on a buzzer, or it needs to do something else. So you've also done like the clock, so it could start a clock, or it could do something else where it is triggering something else to happen in your circuit. Okay, does that make more sense what you're supposed to do for the final project? Okay, any questions on that? Yes? So you can do it in LT Spice, or again, if you haven't been in the lab, you're not as comfortable with that, you can do it in every circuit and do part of it in every circuit where it would do more of the plugging in the different values for the resistors and getting voltages out, and then use those voltages in the next portion, which would be, if it's a digital design, then you could use that in circuit verse. And so, you can use two different simulators if you need to. LT Spice is probably going to be the easier one. I put on that page, I also put a model. So the op-amp is not, the one you're going to actually build with in lab, is not modeled in LT Spice. So you can use the model that is in there that's very similar to it, which is the LT 1014. And so you can actually put that in. If you use a different type of thing, you can look for a model to import into LT Spice if you want. Okay, I think I saw, yes. A what?
Solo project?
Yes, solo project. So you can talk with your friends about the ideas, but then you need to implement it. And if you decide to do something similar to your friend, make it different, make the application, unique. So, all right, any other questions? Okay, so Here's some other, interesting things also on that page that you can also look through. It has examples from the older version of this course, 1240, as far as what some of their project ideas were if you want to go and see those. So if you don't build it now in 1235, you are going to build at the end a final project in there. You can use this as part of it, or you can use it if the only other requirement after this half the semester is that you add in a timing element to it, which is what we're going to learn and talk about for next period. So with that, you would design the RC values themselves to get a very specific timing on a clock, for example. So that could be what you could add into the project if you use the 555 timer. But there's other things you can also do with using the time-dependent elements to actually filter some of your signals instead. So there are some fun ideas that you can add on to whatever you're going to do right now if you want for the final project for in there. Okay, any questions though about the final project? All right, so timing-wise, this Friday I'm going to give an opportunity to work on it in class. So we're going to meet in the Engman lab. So you'll have all the TAs and myself there to support you with any questions. So your proposal idea is due by the end of tonight so that it can get reviewed and okayed before Friday.
How do we submit it? There's not a thing on campus. Do we do it in person?
Oh, submitting nothing. Oh, yeah. Let me change that. Yes. So, sorry, you are supposed to submit there online. Okay. So you could write in there very briefly. Thank you for calling that to my attention. So you should be able to write a small little paragraph in there. On the final project description, it does have specifically what to turn in for this, what your system will do, what sensors you will use, how you will model them in the simulation, and like what other blocks you're going to be using, if you're going to use digital logic or the op amp, et cetera, and that. And then if you use any references, what references are you using? And that, once you get a grade in there, that means that it's been approved and to go ahead. If not, you'll hear from one of us to say, needs to be changed slightly. And we can also discuss that on Friday if there's still questions about it.
Does it have to be accurate? Like, say that I turn it in tonight. What if I want to change my mind the next day?
As long as it's close to what was approved, and that's sometimes what happens, like, yeah, I want to design a watering system, and then as you get going, you're like, oh, it needs to have more specifications than just this. So it's a watering system, but now I have more information about it.
But you cannot change from something.
If you want to discuss that, you can discuss it with the TA or with me, and then just get a verbal approval for the change. Okay, any other questions? Okay. All right, also on Friday, since we're going to have a lot of support there, any questions from previous exams to prepare you for, or any questions for this coming up exam, I can address that, or the TAs can answer any of those questions. So come with any questions you have about the exam on Monday. And then if you have any questions about the final, which will be the next Wednesday, you can also bring any of those questions and we can go through. So there's lots of support on Friday for all of that content. Okay? All right. Oh, I did not post the notes today. Yeah. Little slow. Okay. Give me 1 second while I post the notes. Okay, so the notes should now be on that Unit 3. If you refresh your page, you should be able to get those. So those that are pulling them up, let me know that you get them. Thumbs up once you get them. Okay, got some thumbs up. Awesome. All right. So, and after this Friday, we're going to meet the rest of the time in the Ingman Lab for the rest of the semester, because you'll have the exam on Monday, and then you'll have the final option on Wednesday, and all of those will be in the Ingman Lab. And then you'll do your demos in there also on the next Friday. So starting this Friday, just all next week will be in the Ingman Lab too.
The exam isn't this Monday, it's next Monday?
No, it's this coming up Monday.
This month? Okay.
Yep, so this coming up Monday. All right, so on the exam, it's gonna be digital logic, so combinational logic, so making sure you understand all the terms, like a clock, what does a 0 and 1 mean? What's an analog system versus a digital system? Bit, binary, what does binary mean? Logic gate, what does the logic gate mean? Truth table, finite state machine, states. What do all of those terms that we've now been introduced to with the digital logic, what do they mean? Being able to convert from binary to decimal, decimal to binary, be able to understand logic gates, and then combinational logic. So be able to implement the combinational logic from a truth table, or be given the combinational logic and write the truth table for it. Okay, so being able to do back and forth between those. In sequential, understand asynchronous versus synchronous, understand the components. So the 555 timer for being able to create a clock, 7-segment display, being able to understand, well, what does a high mean? So again, that's part of the terms of what does a high mean? That's usually a 1. What does low mean? That's a 0. So those kind of terms. Understanding a register, latch, flip-flop. For the registers, we went into specific types of registers, and so understand what those are, what they mean. You won't have to design the sequential logic, but understanding what you may need to create the design. So understanding that design flow. So what is a state? That's the other terms in there. What's a state diagram? So being able to visualize the transitions between each of the states. What is a state itself? What is current state versus next state? After that, how do you look at the truth table, understanding what your inputs and outputs are in the truth table? So more of the basics of that versus the actual design. Understanding that for a 3-digit, or if you have 4 states, how many flip-flops would you need in that design? So those kind of questions would be what you can expect for the sequential one. Does that make sense, what is going to be expected? Okay, so we're going to go through examples. So, and I forgot, counters is another one in here. So, add in. So counters, state diagrams, state tables. So those are the other terms that you are also going to need to make sure you understand. All right, so in binary counting, what comes after 0, 1, 1, 1? Anyone? Thank you. Okay, so it would be 1, 0, 0, 0. Okay. Count in binary from 0 to 10. So take a second, write down the numbers. And then I will write them, and hopefully they'll be the same. Okay, did something else wrong. 0, 1, 0, 1. Okay, 1, 2. All right, so remember, when you're doing this, you're toggling this last bit every other one. The next one over goes 2, next one goes over 4, and then the next one goes over how many? Every 8. So it has to do with however many. So man, I'm a little tired. 2 to the 2, and then 2 to the 3, and then the next one would go every 2 to the 4, which is 16, and then the next one would be 32, so on. So it goes by the exponential of 2. All right, any questions with this question? Being able to count, being able to understand what the next number would be here. All right, if these were states, how many flip-flops would I need for this design? Or if I wanted to store 10 into registers, how many flip-flops would I need? Correct, 4. So I need a register for every bit. So I would need 4 registers, or 4 flip-flops. What type of flip-flop would be the most useful here? Correct, D type. Okay. All right, what kind of a shift register is this one?
Serial in, serial out.
Correct. Serial in, serial out. What about this one? I heard somebody say it, parallel in, and what out? Serial out. Okay, good. All right, so say I store 1, 0, 1, 1 as my data here. After 3 clock cycles, what will be on each of these wires? So take a second to try to figure that out. So, in other words, what will I find on A, B, C, D, and E on this one? And then what will be on A, B, C, D, E on this one? Okay, at cycle 1, I'm going to have a 1 here, right? Cycle 2, that's going to shift to this one. Cycle 3, and then you are unsure what's going to be on those, so you would use X's. So that one will be here. The 0, so this would be 1, this would be 0, and then this would be a 1. Would be in these locations. And then it's unknown on D and E after 3. 2, oh wait, no. 1, 2, okay, it would be one more over, sorry. So shift over one more. So it would be, I'm just tired today. There you go. 1, 0, 1, 1. So 1, 2, 3, yep. Okay. So 1, 0, 1, 1 would be located at these locations, and then it would be unclear what D could be either one. And you don't really know because you don't know what's put in before it. Does that make sense? Yes.
So does it mean that it reads it left to right?
So the first one in is going to be, yes, this one first. First bit in. Is that most significant bit. And then coming out would be that first significant bit again as it comes out of it. Does that make sense? Okay. All right, any other questions on this? Yes.
So at 0 clock cycles, the most significant bit is at A.
Yeah, so it would just be sitting before the cycle, before they even start to register, correct. So you would have a 1 on the A first, and you wouldn't, it would be like B, C, D, and E could be some value, but you don't know what they were. They were from something else that was set in there beforehand. So that's why I use that X to mean I don't know. It could be either one. So yes, on the first cycle, A would be 1, and then B, C, D, and E is unknown. Or sorry, before the cycle starts. And then after the first cycle is going to be B would be 1, and then A would be 0. And then second one, C would be 1, B would be 0, and A would be 1. And then the third one would be here. Okay? Does that make sense? Okay, so make sure to understand these for the different configurations. Any other questions on this? Okay. So this is another good one to know, is that you do need to make sure that you're putting in the most significant bit first, and then that gets shifted through. How will the data be, how would you want to store the data here? What value would be PA, PB, PC, and PD? For that 1011 is what you want to store. So PA is going to be either one, that's going to be 1. But what is PB going to be? 0, correct. So you want to make sure your most significant bit is going in as it comes out first. 1. So this is how it looks before the clock cycles, so clock 0. And then after the first clock cycle, you're going to have a 1 here, a 0 here, 1 here, and 1 here. And then the next clock cycle, you're going to have, this one will be shifted out. This becomes a 0, 1, 0. And then this is now kind of unknown. And then the third clock cycle, you're going to have the 1, 0, and 1. So these will be what will be remaining on that third clock cycle. You'd have a 1, 0, 1 there. Yes?
Where you getting that extra zero from?
Which extra 0? So first clock cycle, I'm sorry, I'm going to read this one. 1. Okay, I don't think I did this right, did I? Okay, second clock cycle, that would be a 0. Okay, I see what you're saying. I don't know what I did. Let me go back. Okay, first clock cycle. One, 1, 0, 1. Okay, first clock cycle, you read a 1 on E. And then the second clock cycle, you're going to read a 0 here, and a 1, and a 1. And then the third clock cycle, you're going to read a 1 and a 1. There we go. I see why you were confused. Okay, does that make more sense? Okay, sorry about that. I don't know where that 0 came from. My late night last night, I think. Okay. All right, any other questions on this one? So do make sure you understand like what's happening in each clock cycle and what's going on with these.
So is A unknown the whole time?
So when you actually do this, you put the values 1, 1, 0, 1 on there, and then you actually take them off after. And what the MUX does is it senses that you don't have data on this line anymore, and then it's going to read whatever A was. So you don't know what A is because it's kind of shifting in from something else too. So it will be something, but it will be, kind of an X because it could be a 1 or 0, which doesn't really mean anything. So correct, the whole time it won't be anything.
Is it important at all to know how the flip-flops work on the inside or just
Nope.
how they shift?
Just kind of how they're shifting, yeah. Yeah, I won't make you understand the inside of them. That digital logic is a little confusing because of the feedback that it gives itself. So yeah, more understanding that it's just holding data and kind of acting as a memory. So I want you to know that higher level, and then kind of more of this understanding of like when you're talking about parallel in and serial out, how does it read the data in and then how does it come out? Because that's going to be what you're going to need to know as you move forward in the next classes. Okay. All right, other questions? Yes.
So on the first clock cycle, it's loaded A to D, and then on the second clock cycle, it'll be D to E.
Yep, so it moves it in first clock cycle, it goes onto the output of the latches or the flip-flops, and then it shifts it along as it goes until you have a new number that wants to be stored in there. Okay. All right, other questions? Okay. All right, another type of problem could be to create the combinational logic. So last time we did X, so this time I thought we could do Y. And so take a minute to create this combinational logic. process, right?
So are we gonna do like what logic we use or?
If it's a single logic gate or a combination of logic gate to produce that.
Okay.
So it has 3 inputs and 1 output.
The XOR gate is actually.
So 3 input and the XOR gate is very confusing.
No, just actually be
Between B and C, let's see what that works. So if you note that, oh, well, I kind of notice a pattern here between 2 of the inputs and then it doesn't matter what the 3rd input is, you could use just a single XNOR gate between B and C. And you can check that. The XOR gate does when they're the same, you get a 0 out. When they're opposite, it's a 1 out. And you can see on those that it's opposite there. So this could be just one single XNOR gate. If you don't see that, you could also implement this as A bar, B bar, C bar, ORed with A, B naught, C naught. I lost it. 1. Or A, B bar, C bar, or ABC. You could then simplify these by noticing that, combining those. Oh wait, I wrote the same ones. Sorry. ABC, A bar. Okay, I missed A bar, BC. A bar BC is the one I missed. So you could see like, okay, these 2, I have A bar A. So I could factor out BC from these and do A bar or A, which is always a 1. And then here I see that I have BC. And then again, A bar or A, which is going to give me 1. So then I have B bar, C bar, or BC, which I can then say like, oh, that looks like an XNOR function and do it that way. Or I can create the logic for all of these. And you would get credit for either one. So you're not required to simplify it if it's not asked to be. So here I could implement this XNOR gate as 2 AND gates, and this would be B bar, C bar, BC. Or I can do all of these, which would be all into a 4 input OR gate. So any of these are correct. Any questions about creating the digital logic from a truth table? Okay. All right, what does a truth table represent? Correct, all possible input-output combinations. So it gives you that information. What component is used to generate a clock signal? Correct, the 555 timer. Convert the following decimal number to a binary number. This is an easier one. So you shift it over, so it's going to be 0, 1, 2, 3. Is it to the fourth?
Yeah.
2 to the fourth? Yeah. So 1, 0, 0, 0, 0, 0. So there would be your 32.
Supposed to write it 6 bits.
Oh, thank you. 6 bits. 1, 2, 3, 4, 5, 6. Yeah. So again, you can go through this if you don't remember that. So 2 into 32 goes 16, remainder 0. 16 divided by 2, 8, remainder 0. It's 4, remainder 0. 2, remainder 0, and then 1, remainder 0, and then 1 divided by 2 is 0, remainder 1. Oh wait, 1, 2. Sorry, I'm missing one more. Oh. 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. 2 to the 5th is 32. Okay.
Would it only be 5 zeros after? So 1.
So this will be 1, 2, 3, 4, and 5. 2 to the 5th is 32. Two to the 4th is 16. So this is 1, 2, 4, 8, 16, and then 32. Okay. Did the same thing I did. Okay. All right. Other questions on this? Okay. Practice your math so that you don't make the same errors I just did. All right. Convert 37 to binary. If we are, and no, we already know 32 because we just did that one. So what would you need to add to it? 5. So how would we add 5 in there?
4 and 1.
4 and 1, correct. So it would be 4 is the third one over, and 1. Questions on that? All right, what kind of a gate is this for a single gate? Correct, it's an OR gate. Which logic gate outputs true only when both inputs are true? I heard somebody say it loud. AND gate, correct. All right, what single block will be E to give you X? So that's going to be C input, and then an A bar right here. So I do want to make sure that I write that so I don't make an error. So what will give me the output? It was X, right? X. So an AND gate would give me that output. All right, any questions on these? All right, what is the output of the following circuit? So when I have a 0, 0, what do I get out of here? I'm going to write these next to it just again so I don't make errors. I'm going to get a 1. Correct. So correct, somebody said that it is a NAND gate. Okay, an asynchronous input entering a synchronous system should be synchronized to the system clock, correct. So you need to make sure when you're moving from an asynchronous input, that means that synchronizing it is we time it to clocks. So we just have to add a clock into the system. In 555 astable mode, the period is set by which? The external R and C values, correct. A truth table for 7-segment driver maps. Correct. The 4-bit input to 7 outputs, A through G. Which combination on the 7-segment decoder, meaning it's an active high, will turn this into a 0? Correct. We need to have A, F, E, B, C, D, everything except for G to give you the 0. This one. So that would give you a 0. Which flip-flop is best suited for counters?
The JK, yeah.
Correct, the JK flip-flops. Implementation of a finite state machine typically uses logic gates with flip-flops. So that's what a finite state machine will look like. What happens in the finite statement if an incorrect input is entered? It goes back to the beginning. If it continues to the next state, is it working correctly? No. Okay, good. If it unlocks it, you press the wrong number and it unlocks it, bad system. If you store that information in there and it doesn't do anything, that's also bad. So not working correctly if your finite state machine is doing those things. Which type of register is used for temporary data storage? Correct, that shift register. All right, how many flip-flops are needed to store the number 10111? Correct, 5 flip-flops. How many flip-flops would we need to store the decimal number 11?
4?
So, yeah, sorry, I didn't notice that, but yes, decimal number 11. So what is the decimal number 11?
1011.
Okay, so we need 4. Okay. Okay, so that's kind of what you will expect for the sequential kind of logic and for the digital logic. So make sure you understand all those concepts, and then Unit 3 practice will give other ones that we haven't gone over. So they give you additional practice. I suggest doing Unit 3 practice a lot. Make sure you're really understanding all of the concepts there. So I had a request to go over kind of the state transition table and how you work into this, from this into the actual digital logic of it. So remember, what is a current state? Actually, let me get the state diagram too. Okay, so first off, how many states does this system have? So we have 0, 1, 2, 3, and 4. So it has how many states? 5 states. How do I write 5? The number, decimal number 5 into binary is 1, 0, 1, right? So how many flip-flops am I going to need for this? 3. Okay. So knowing that I need 3 flip-flops because I have 5 states, I then want to code each state with a binary number. So I can use 0, 0, 0 for S0, which is state 1. State 0, and then state 1 is 1, 0, 0, 1. State 2 is 0, 1, 2. Sorry, 0, 1, 0. State 3, 0, 1, 1. And state 4, 1, 0, 0. Okay? So with that, I know I need to have those 3 bits. Then I need to know, like, how do I get from current state to next state? So I know I'm going to use those flip-flops in there. And how the flip-flop works is that I'm going to have my digital logic. I'll call it logic 1, logic 2, and logic 3. I'm going to have basically inputs into these, and then they're going to get stored into the flip-flop, and then out of the flip-flop will be what I'll call my current state. Before the flip-flop will be my next state. So now I want to shift gears in my mind as far as, well, how do I encode this into that structure? So I want to look at each bit individually. I'm going to call the first bit kind of my current state 1, the next bit current state 2, and my third bit, and I labeled them C1, C2, and C3. So you can label those kind of any variables that you want. So these are going to be my inputs and then my output for the digital logic, right? So into my digital logic, which is here, I'm going to actually have going into those my output is this next state. So output of that portion is the next state. So going into it can be the current input and then my input button, which I called X in this case. So going into each of these is that current state, which is being fed from each of these. So this looks weird because you're getting the feedback going back into them. I also have then also going into each one of these that X input. So that's the digital logic portion. And so now I need to know, like, okay, this is my inputs, and this is my input. And then the next state is my actual output. And out of each one of these is, again, 3 single bits. So I need to first do one of the bits. So I would call like N1. What do I need for N1? Well, it's going to have all 3 of these variables, which I labeled C1, C2, and C3. And then there's all of my variables X. So on that, I then look at when I have a 1, which is just right here. And so that is only going to be this one case here. And I do this just like any other truth table. It would just be that N1 is going to be C1 bar, C2, C3, and X. And so that's what's going to be in that logic portion of this in that first box. Does that make sense? Does that help?
X isn't unknown, right?
X was your input, the digital, this was, remember that digital lock? And so the X was what was pushed on the digital lock. Did I push a 0 or did I push a 1? So that's what that part is. So this is your, from the keypad, what was pushed. Okay. All right, I had some questions on this. People were still seem to be a little confused. So I want to make that clear. What you need to take away from this is understanding that if I was trying to get my next state, that would be my output. My inputs would be my current states that are coming from that flip-flop. And they are being tied back around. Does that make sense? Okay. I know it seems a little bit weird to grasp. All right, any other questions? You guys want to end a little early? Okay. All right, I have not posted the quiz for today, so no quiz today. Go instead and work on more practice problems for Unit 3. So work on that and get some extra practice to prepare for the exam. And then I'll see you guys on Friday.